Welcome to today's webinar, HESO-LP hands-on optical and laser testing with large pupil wave sensor. Thank you for joining us. My name is Omar Kuwaiter and I'll be your host for today's session. We're excited to have you as we explore the capabilities of HESO-LP. That will show you how it can enhance your optical and laser testing process. So following is the agenda of the webinar. We're going to introduce briefly Imagine Optic and present you the product, HESO-LP, along with a live demo and a Q&A session. We encourage you to ask questions throughout the webinar. We'll have a dedicated Q&A session at the end where our speakers will address as many as possible questions. So for those of you who may be unfamiliar, Imagine Optic has been a pioneer in wavefront sensing and optical metrology since 1996. We are a privately owned company, technology dedicated to developing and manufacturing high performance, versatile solutions for a wide range of applications. We have more than 30 patents and we are a team of more than 60 people. In 2003, a sister company was created, Imagine Eyes, dedicated to ophthalmology, and in 2024, Shocklight was created for laser shock feeding. And following are our base of clients in optical metrology and optical correction. So what we offer at Imagine Optic, we have two different offers, the analysis and the control. In the analysis part, you can see on the left side the wavefront sensors and the metrology systems. And in the metrology systems, you have different solutions for your production line and other systems for your metrology labs. On the right side, you can see the formal mirrors dedicated to different applications like high power lasers and microscopy, ophthalmology, and laser beam shaping. And the other adaptive optic solutions like Chow, which is dedicated to astronomy and SATCOM. I will leave the word to my colleague Rafael Porcar, scientific coordinator at the company, and Diego Ormaechea, application engineer. The floor is yours.
Thank you, Omar, for the nice introduction. So I'm Rafael Porcar, scientific coordinator in charge of optical metrology activities at Imagine Optic. Our portfolio for this activity consists in both sensors and instrument being sensors coupled with illumination path and accessories, different kind of optics to adapt beam to the specificity of the sample you need to characterize. If we zoom in the sensors part of our portfolio, you can see roughly four main categories. On the left hand of my screen, we have all our sensors with ultra high resolution based on lift phase retrieval reconstruction. On the center part, we have our standard Shah-Karpman wavefront sensors for the visible range, broadband spectral range, and at the bottom, 3 wavelengths. We also offer some customer-inspired wavefront sensor for high-demanding application. This is our Edge series, and one of the latest incorporation of our catalog of products are the CAM squared, which are dedicated to laser beam tested and M square parameter characterization. But let's focus on the latest addition to our catalog, the HESO-LP that you can see here on in red in the screen. So What does LP stand for? That's large pupil of analysis wavefront sensor. So as such, it's a sensor which is perfect for the obviously characterization of optics, both end of line testing if you are a manufacturer and you want to check that your parts um, uh, respect the specification you established, or if you are an integrator at reception, you can use it to test your optics before embedding them in your system. You can use ASO-LP for laser beam testing, or optical system alignment, meaning system composed of many optics when you need to optimize the alignment of one respect the other, or to adjust some specific parameters such as the focusing distance respect with one element, or collimation for example, which is a very good application of the ASO-LP. As a Shah-Kaufman wavefront sensor, it benefits from the advantages of the technology, meaning that you can perform live measurement thanks to the very short acquisition time. It's microsecond, tenths of microsecond acquisition time. So it's live, and it presents the advantage of freezing, let's say, vibration or atmospheric turbulences, making the technology very robust to harsh environments. As all our products, it comes with standard accuracy in absolute mode of lambda over 100 root mean square, sensitivity lambda over 200 nanometers. So that's really high accuracy. And it's calibrated in factory, meaning that when you receive it, no need for calibration, you can directly measure absolute tilt and absolute wavefront. And the technology is also, sadly for our competition, highly achromatic on the whole range of the camera, and we'll be able to dig a little bit in this aspect, the Q&A if you want. So what makes the ASO-LP unique? As the name says, it obviously that's the large pupil of the sensor. It's 22 by 22 millimeters squared. So that's really an important pupil size. And to put it a little bit into perspective, here you have a representation of the pupil size compared with what was so far our bigger wavefront sensor, the ASO 126, which is quite a big sensor with a 10 by 15 millimeter square pupil, and you can really see how big is the new pupil of the sensor. So what kind of advantages does that bring, having a large pupil? Mainly, it means that you don't need relay optics anymore in order to adapt the size of the beam you need to characterize to the size of the analysis pupil of the sensor. Meaning you don't need to design some relay anafocal, for example, or beam reducer of some sort. You don't need to mount and align it in front of the sensor, and you don't need to calibrate it anymore. And that means saving time, not one time for the design, but every time you need to set an experiment. And also, it really is a way to improve accuracy of the sensor. And that's the topic of my next slide. So if you have to design a system to adapt the size of your incoming beam to the size of the analysis pupil of the sensor, you will have to take into account aberration of the different optics that they bring to your measurement, and that does not correspond to your sample or to the laser beam you want to characterize, you have to take also into account uh, the alignment of one respect with the other. Depending on the wavelengths, you might have or you might have some doubt on the perfect collimation, and you might need to readjust it and recalibrate it each time. And also, you can have some doubt on the perimeter of validity of this calibration, meaning that if um, uh, your beam is coming in a slightly different configuration than the one you take the reference with, you might introduce some relative aberration that again limits the accuracy of your measurements. If you remove this afocal, you remove any doubt, you remove any problem you may have with this relay optics, and you truly benefit from direct absolute measurements. No question asked. So that's a big advantage of combining large pupil together with high accuracy. So I'm also going to precise a little bit the advantages of this combination of features for a very simple application, which is the adjustment of the focus distance of your system. So the wavefront sensor is measuring the wavefront error, meaning the departure, the difference between the sphere and the plane, as you can see, and the more you propagate, the bigger the radius of curvature is, the flatter, let's say, is your wavefront error, and it becomes flatter and flatter and flatter. So if you want to be able to distinguish a very small sphere component of your wavefront, meaning large radius of curvature, meaning very highly collimated beam, you really need to have a phase resolution, this lambda over 100 absolute, to do so. So that's the first point. A second point comes from the large pupil. So if you consider a standard pupil wavefront sensor, so the sphere is creating a difference from the plane, which might be small and which might be smaller than your phase resolution of your sensor. Now, by enlarging the pupil of your sensor, you let you let the sphere component be larger and be above the threshold of the accuracy of your sensor. Indeed, the peak to valley of the sphere relates with the quadratic size of the sensor pupil, meaning that the radius of curvature is also relating with the quadratic size of the pupil. So if, for example, you multiply by 2 your pupil size, you will multiply by 4 the sensitivity on your measurement on the radius of curvature. So that's a unique feature obtained by combining both large pupil and high accuracy. But ESO-LP is not only to measure, let's say, flat wavefronts, because we also we did not sacrifice on the dynamic range to achieve this accuracy. And here is an example of the dynamic range you can get for every aberration of the wavefront, and you can see we are over 1,000 lambdas of tilt of astigmatism. We are above 600 lambdas of focus or trefoil and so on and so forth, which is really a high dynamic range. And all these characteristics are combined also with large resolution that we can achieve thanks to the lift phase retrieval reconstruction I mentioned. So lift correspond to algorithm we further developed at Imagine Optics that allows us to multiply the spatial resolution, the sampling of the phase by a factor of 16 time. And that allows us to offer the ASO-LP with a 512 by 512 phase points. So ASO-LP is proposed in different versions. We have visible versions that correspond to a bandwidth of 400 to 800 nanometers. We also have a broadband version for customers that span a large range of wavelengths and goes from 400 to 1100 nanometers. And we also have two different versions of sampling, 128 by 128 phase points, or the lift version, which is, as I said before, 512 by 512. Sensors embeds two patents we have, one for ensuring that intensity and intensity variation across the pupil is not affecting the accuracy of the phase, again to offer you the best accuracy possible, and also the spot tracker, which is an algorithm that allow you to measure absolute tilt without any type of setting. So in order to conclude my talk, I would encourage you to download the datasheet or request a pre-quote from our website. And for those of you that will visit Photonics West, come and say hi. We'll have a booth and we'll be very pleased to discuss with you about your wavefront sensing applications and need. So the floor is yours, Diego, and I was wondering if maybe you could show us a little bit the wavefront sensor and maybe demonstrate the accuracy of the wavefront sensor.
Of course, we can start with that. So hi everyone, thank you Omar, thank you Raphael. Now the camera is active. You can see a little setup. I hope so. So here we have the HSO-LP that we are showcasing today, and a small breadboard with a fiber output at the other end. We use only one wavelength, which is at 1050 nanometer. And first, let's start by showing that our absolute accuracy is lambda over 100 RMS. How to do so? So the idea is to measure a perfect spherical wavefront, and by removing then the curvature, theoretically we're gonna have a RMS wavefront which is close to 0. In our case, close to lambda over 100 RMS. So I'm gonna share our software, WaveView. So WaveView is our metrology software. Now I'm sharing my screen. And the first part is to get a camera signal. Now I'm launching the acquisition. We can see at the bottom of the screen the camera signal. We have an image saturation between 80 and 90%, which is optimal to have to get a reliable wavefront. So it's the main window in the center of your screen. Actually, we can see that from this fiber output, which is almost a point source point, we get perfect spherical wavefront. If I display it in 3D, we can see this curvature. So we have some curvature, that's logical. So here at the bottom right of the screen, I zoomed on the main matrix we are looking at. So curvature, wavefront PV, wavefront RMS. If we go on the left with the settings, we have the averaging. For the moment, it's only 1. That allows us to have a frame rate of 10 Hertz, which is optimizable, but now we are showing the screen and everything. And the exposure time is, as Raphael mentioned it, microsecond. For instance, here we are at 600 microseconds. Now, we have the possibility to filter some aberration, for example, the curvature, so the best fit to the sphere. I'm doing it. So now, theoretically, I have no aberration. In this case, we can see that the wavefront RMS is below 20 nanometers. Our source is 10-15 nanometers. Divided by 100, we expect to have a wavefront RMS around or below 10-11 nanometer RMS. We are with ambient light, with some air turbulence. That is why the value of wavefront RMS is fluctuating. Now, if I remove the background, so the ambient light, we're gonna get a more reliable measurement. And to cancel or reduce the effect of air turbulence, we can average a little bit. For example, let's go from 1 image to 5. Now, if we follow this value of wavefront RMS, we are below 10, 11, 9. That's almost good. And if we increase the averaging, we're gonna get a value which is more stable than that. If we plug it over time, we can see that the mean value is 8 nanometer. So first thing, demonstrating our absolute accuracy is done. Now let's go to real application and to what extent the HSO LP can be useful. So to do so, I'm going to stop the acquisition. The idea is, for example, to align a collimator or collimate a beam. So here we have the fiber output. Here I have a long focal length. So the focal length is 200 millimeter. I'm gonna install it on the bench, as you can see on the camera. I'm gonna launch the acquisition. First step is to watch the camera signal at the bottom of your screen in order to see that we have some signal here. I will try to center it as much as possible, a little bit higher. Let's say it's good enough. So now, second step, that my beam is on the camera, is to get an optimal value for the raw camera image. To do so, I can play on the exposure term of the camera. Here, I'm going to play with the power of my source, which is an Imagine Optics source, superluminescent diode at 10-15 nanometer that can be controlled remotely thanks to its software. So you can see the value of image saturation that is fluctuating and trying to reach between 80 and 90%. That's done. Okay. So now I have a reliable measurement for the wavefront. So here I can see my wavefront. If I unfilter the curvature, we're gonna see it. So we can see that there is clearly some curvature in this collimated beam. Now we are not looking at the wavefront RMS, but to the curvature. The inverse of this metric is the radius of curvature of your beam. So now we are 0.3 dioptries. If I translate my lens, so I'm moving, so the lens is on a rail, I'm gonna translate it and trying to reach 0 to cancel the curvature and to get a collimated beam. So that's what I'm doing now. Okay. Okay. So I'm almost, I have almost canceled the curvature. Well, not that much. You can try to do better. Something like that. Not that bad. Oh.
You have to take the background also.
Yes, we can remove the background. Maybe there is much more light. No, remove it. Okay. Now there is more light with this focused beam, so we can not use the background. I'm gonna increase a little bit my power.
So here, Diego, as we are working with ambient light, we have the option to remove background, which is noise from the room that might affect the measurements. And if you change the condition of the experiment, you have to retake the background, which is what you just did, no? Somehow.
Exactly. So in this case, I remove it totally. So on the left here, you have subtract dart. Because we have enough light, enough contrast on the raw camera image, I can work without it. If I use a background now and subtract it, I'm gonna get a more accurate measurement. But for what we are doing, we can do without. So let's go back to this curvature, trying to cancel it. Something like that. You have to be gentle. Path. Okay, okay, not that bad. So now we can see on the wavefront window that there is no curvature, or very few. What we can see is something that may be spherical aberration. Another thing that we can do, again, is to follow the curvature over time. You can see that the value is fluctuating because of air turbulence of the room. If we increase the averaging by to 10 images, for example, we're gonna get a slower software, but a value which is more less fluctuating. That's it. So now I'm gonna stop the measurement and showing you another way to collimate. So there is two possibilities. You can use the zonal reconstruction of the wavefront and this value of the curvature. Another way to do that is to use Zernike polynomials. So in WaveView, you can choose the kind of reconstruction you want to use. So here is the zonal one that helps you to reconstruct any shape. With the Zernike, which is a model reconstruction, you need a circular pupil. So now you can see on the wavefront this circular, this circle, blue circle around that display the pupil you are working on. And thanks to that, we can have the Zernike polynomials. I'm cleaning up a little bit the displaying. Okay, and with Zernike polynomials, we can see that the third coefficient is the focus. And that's the second way to collimate and align a collimator is to focus the alignment on this value, the focus according to Zernike instead of the zonal reconstruction of on the wavefront. So if we go back to the live acquisition without less averaging, path, I'm gonna remove the focus. So maybe I can zoom on this value to help you to follow what I'm doing. And here, now removing the focus, we can clearly see a spherical aberration again in the center. That's how a wavefront sensor can help you to align collimator or to just characterize a beam and say, is it collimated, to what extent it is collimated.
Okay. So then, with this same kind of beam, what would happen if we were working with a smaller wavefront sensor? As I was highlighting, the interest of having a large pupil for the sensor.
You're gonna lose accuracy. As you mentioned, HSOLP is interesting about the large pupil, but this large pupil allow you to get more accuracy on your measurement and in your wavefront measurement. So here, I'm gonna display now the wavefront in terms of 2D profile. We can clearly see the shape of the spherical aberration in both axes, X and Y. Now we're gonna simulate, because it's faster, how this wavefront would be measured by a smaller wavefront sensor. To do so, I'm gonna use the mask editor of WaveView. So on the top, on the window, I click on the mask. I can see my pupil. I'm gonna switch off all those subpupils. I'm gonna define a new region of interest, which has the same size of our previously largest sensor, the HSO 126. So this HSO is 10 millimeter by 12 millimeter path. So we can see the difference of size, and I'm trying to center it. Now, remember this shape of spherical aberration that we were seeing on the screen. Now, it is clearly seen as curvature. And if I put in zonal, it's even more visible. You can see that a smaller wavefront sensor, if we do not put any afocal system or beam reducing optical setup, gonna measure that. So a lot of curvature. If I put it in 3D, it's obvious. And if we display the value of curvature, here we can see that it's not 0. So that's the main risk. So here
we cannot pretend performing a good collimation if we don't take into account the whole beam of the sensor. We really have to implement some kind of strategies if we have a small pupil sensor.
Exactly, and that's so the main thing is to not measure directly a beam which is larger than the wavefront sensor. You have to get the entire pupil inscribed on your wavefront sensor. And it's almost the case here for this 1-inch beam. So I clear now my mask, get back to the real pupil size of the HSOLP, sorry, and we get back this spherical aberration, and that's the main point. So the large pupil help us to get accuracy and collimate in an easier way our beam, our collimator, our laser, or anything else. I hope it was clear.
Thank you very much.